All right, so we're getting ready for our next class. This one is again essentially looking at two systems which we've combined into the musculoskeletal system. So we're going to be looking at skeletal muscle and we're going to be looking at the skeletal system. A and P again is going to break these two apart, but we're going to talk about them in conjunction since they work in such a symbiotic relationship to allow you to be able to from a skeletal standpoint, obviously we're referring to your skeleton, which is comprised of all the different bones within your body. They provide a couple of different major things, not only protecting all your internal organs, but also creating the structure or the rigid components by which we actually move. So how do we move those bones? Since they're just a passive, rigid structure, though, is the musculo portion of the musculoskeletal system. So these are your muscles. And we have a tendency to primarily focus on skeletal muscles, although there are different forms of muscles from cardiac muscles and smooth muscle and skeletal muscle. There are variations within each of those as well. But for the most part, we just at this intro level are talking, and through much of exercise science, are talking about skeletal muscle unless we clearly denote otherwise. So the skeletal muscle is going to connect to bones, and it is their capacity to contract and create force that allows the movement of your body and allows for all of the magnificence of the things that you are able to do, from writing in cursive to throwing a javelin to swimming underwater to et cetera, et cetera. I mean, all of the beauty and majesty and creativity that you can do with motion is predicated on the interaction of these two structures, or these two systems. So we're going to get to know them just a little bit better. It is muscles that are actually creating torque, which is a force or a rotational force around an axis. So we're going to see that since we have the two rigid bones stuck together, as they move relative to each other, as they shift and adjust, that they're moving around an axis point. So, and torque just means that we're creating force around an axis point. So, starting with that skeletal system, then from the bone standpoint, bones we oftentimes think of as just being this really rigid and hard structure, but they're way strong. Well, they're not way stronger. We already recognize them as strong. They're very strong, but they're also a lot more flexible than we typically recognize. So they're composed about 45% of mineral content, which of the two primary minerals that we're housed or comprising our bones out of are both calcium and phosphorus, but there are others. It makes them really strong, but that mineral component is what creates some of the brittleness of them, of not binding, not having a lot of give because of that mineral structure. But if you think of minerals, like an analogy could be rocks. Rocks are really, really strong and can really withstand some, especially compressive forces. So when we're pushing things together, they're really, really capable of handling those kinds of forces. And that's what happens a lot with our bones, because we have all the mechanical loading of just your own body weight pushing down on your bones constantly. It's not the only kind of stress that your bones face, though. So you can see all of the different forms of mechanical loading that a bone can go through and is going through all the time. From compression, which you can think of like your body weight pushing down on your long bones as you're standing, to tension, which you can see from the illustration is sort of a pulling apart or trying to distract those bones. The one that our bones really seem to have the hardest time with is actually a shear force. So when we have forces that are acting, especially on long bones, in contradiction to the length of the long bone or in opposition to the length of the long bone, that seems to be where our bones are most prone to injury. Torsion is a rotational force, and then bending is bending. Beyond the mineral content of our bones, which is the bigger component of what our bones are made of, it's not exclusively what our bones are made of. We're not all brittle material. So what's going to give it some of that flexibility is the collagen and some of the ground substance, which comprises about another 35% of your bones. It's weaker, but it is definitely more flexible. and allows for more, not elastic, but a more flexible structures. When we think about how bones are actually made, we're taking a look here at a long bone. So bones actually have two primary components to most of them, not all of them, but especially when we're talking about long bones, this is some pretty common characteristics that we are going to be looking at. The cortical bone is that really, really dense outer shell. So as you're looking over here at the illustration, this outer shell that just, there's no porosity to it, there's no gaps, there's no spaces, it's just really, really hard, rigid bone. That portion of the bone is what we refer to as the cortical bone. Within there, however, in our long bones in particular, we have this area is referred to as cancellous bone. So this cancellous area is made up of trabecular bone, or has all of this weaker trabecular sort of structure. So it's got this matrix within it of bone structure, but that also means that there's lots of open spaces and open gaps for the vascular system and for bone marrow and for all kinds of other things, as well as just to reduce the overall weight of those individual bones. So there's a lot that goes into bones, and as you're in A&P and learning about Wolff's Law and osteoblasts and osteoclasts and all of that, that's a fascinating mechanism by which your bones are constantly being restructured and reformed. And I think you'll find that the bones are really a lot more interesting than you think, or than maybe you have thought of before. They're very alive and very, very much more important than just thinking of them as this rigid stick or structure that's sort of holding you upright. Anyway, as we continue on thinking about the skeletal structure, where bones come together, we know of those as referring to as joints. In many of the joints within your body, they're actually covered, where the bones are meant to come together and are meant to interface or to be able to rotate or move or shift relative to one another. We want to make sure that really hard bone structure isn't constantly degenerating, degrading, rubbing itself down, creating problems. So God created you with massive intent and design, and one of the ways that shows up is all of those synovial joints, which is this kind of joint where we're going to see bones moving relative to each other, are covered in, as you can see in this illustration here, there's this synovial capsule. So there's this external, really fibrous, really hard capsule that just sort of keeps everything inside. But what's inside is the synovial fluid. So you have the synovial fluid that separates the two bones and sort of acts in a whole bunch of different fashions to be able to reduce the stresses. So when those bones try to come together, or when there's compression, like if you jump in the air and the bones sort of separate away from each other a little bit because you don't have the weight of your own body sort of pushing through your skeletal structure, then as you land and all of that weight comes back together, the synovial fluid is going to act to dampen, kind of like the shocks on your car, and try to avoid some of the high pressure points for the individual bones. The bones are actually covered in a special kind of cartilage called hyaline cartilage. So it's really super smooth, really super strong. And you can think of it, or I like to think of it anyway, as like two pieces of glass. They're just so, like glass, when we think of it, it's going to be a flat plane, but these hyaline cartilage is just going to cover the surface of the bone. The analogy is meant to be that they're really dense, they're really smooth, they're non-porous. And if you've ever had, like, if you've worked in chemistry, if you've worked in biology, or you've done anything where you've had two like pieces of glass or two really strong, smooth structures, and you put just the tiniest bit of fluid between them, those can move relative to each other with almost no friction, no resistance, no challenge, no problem. And that's the way God made all of the joints in your body, is to function that way. So they're just amazing in how they work. So those hyaline, or that articular cartilage, is covering all of those synovial joints. It's really mostly fluid. Like, we're talking about a lot of fluid. We again are going to see a lot of collagen to create the structure that's around here. You'll notice up in the description that it says it's avascular. So we talked about prefixes and suffixes and root words in past lectures. And we've encountered the A or the AN as a prefix. And we saw it as anaerobic, if I remember correctly. So that was representing the A, or the AN is representing not present, not there. And then there's the root word. Well, you can see in this one then, vascular we're already familiar with. That's going to refer to blood flow. So if it's avascular, that's going to mean that there's no blood flow to this